Hello Legacy Sabers, Marsh here. So today we're going to talk about imaginary and complex numbers. What you're going to have on you. You're going to want your notes, you're going to want a pen or a pencil, and then maybe a calculator for some simple math today. So, once upon a time, a man sat down to solve a quadratic equation, similar to what's on the screen. And he went, well, first I gotta subtract 10. So then he'll get x squared equals negative 10. He's like, well, then I got a square root. And then he said, well, x would be equal to, and he saw a negative under his square root. And he went, I can't solve a negative under a square root. That's no solution. So he did not like that. He didn't like the ability to not be able to have an answer. So what he did is he developed a plan. He invented a new kind of number system and new types of numbers. And imaginary numbers were created and born in about the 1600s. So this is definitely not a new topic. Rene Descartes, that's the guy who found imaginary numbers and who created them. He is credited with the discovery of them. So, what are imaginary numbers? Well, we know that I is equal to the square root of negative 1. That is what I is equal to. So, that means that I squared is equal to negative 1. And here's the reason. Well, if I take I, which is the square root of negative 1, right, and I square it, aka I take the square root of negative 1, which is I, and square it, well, the square root and the square, they basically cancel each other out. So I'm left with negative 1. This is especially important when we start to simplify square expressions with I in a little bit. So, how do you use I to rewrite square roots? It's very common when we want to solve, we want to be able to solve and get an actual answer. So I got the square root of negative 25. Well, what we're going to do is break that into two square roots. So we got a square root of 25 and the square root of negative 1. Because if I want to break down a square root, I can make it and multiply the two numbers that multiply to give me that number. Well, the square root of 25, we know that that's 5, right? And the square root of negative 1, well, we just talked about how that is just I. So 5I is equal to the square root of negative 25. Those are equivalent expressions. Let's try the square root of negative 6. Well, first of all, I'm going to break that into square root of 6 and the square root of negative 1. Square root of 6. Does that simplify at all? Can I take a perfect square out of there? No. So I know this will be the square root of 6. Square root of negative 1, that's just I. You can either leave it like this, or you can write it like that as well, since I is in the front. If you write it like the first way I have it, sometimes the I gets under the square root, and then it looks kind of odd. So be careful with that. Square root of negative 40, well, I can break that into square root of 40 times the square root of negative 1. Well, 40 breaks down, right? What's the biggest perfect square that can go into 40? I think 4 and 10, because 4 times 10 is 40. Well, in the square root of 4, that's just 2. So technically the square root of 40 is equal to 2 square roots of 10. Like that. 2 times the square root of 10. And then times I, which simplified would be 2I times the square root of 10. Let's try a couple extras. I got 5 times the square root of negative 48, so let's break down the square root of negative 48 here. So that would be 5, bloop. Square root of 48 times square root of negative 1. 48. 4 goes into 48. I bet there's a bigger perfect square, because I want to find the biggest perfect square. 1, 4, 9 doesn't go in there. 16 does. 16 times 3 is 48. So this is the square root of 16, square root of 3. Square root of 16 is 4. And we know that's I, right? Square root of negative 1 is just an I. So technically this inside is 4i square root of 3. Multiply my 5 by that 4i, and we'll get 20i square root of 3. Let's simplify this one here too. Can I have a fraction under a square root? It's like this big, like, no, can't have that. Kind of like saying please, not saying please and thank you. Kind of that bad. So what you're going to do is break this into two pieces. Square root of negative 10 over square root of 3. So basically I can take this square root and put it on the top and the bottom. Square root of negative 10, well that's just I square root of 10, right? Over the square root of 3. Now, you can't have square roots on the bottom. Another big no. So what we're going to do is we're going to multiply by a fancy form of 1. AKA, we're going to multiply the top and the bottom by the square root of 3. And it's always going to match the denominator of the original. Well, top now will be I square root of 30, right? Because 10 times 3 is 30. And then square root of 3 times the square root of 3, that's square root of 9. Square root of 9 is 3. That would be my final answer. And always double check, guys. Once you do that, double check that the number under the square root does not simplify even more. Sometimes it can. In this case, 30 doesn't have a perfect square, so we don't have to worry about it. Now, how do you simplify complex numbers, aka having real and imaginary in the same problem? Well, we got a couple of examples here. We have first just addition and then one of multiplication. Addition is the simplest problem ever. All you do is you add reals to each other and you add the imaginaries together. So in this case, we're going to take 3 and add 4, 7. Then we're going to add 2i and negative 6i, negative 4i. That's it. That's the finished product of my answer. Definitely an easy problem. The only thing is, with the subtraction in the middle, make sure you distribute that negative in, and don't forget to subtract. Multiplication, just like normal, you're going to FOIL this. So 3i times 4, that's 12i. 3i times 5i, ooh, that's a little different. So that'd be 3 times 5, 15. I times I, that's I squared. 6 times 4, that's 24. And then 6 times negative 5i, that's negative 30i. Okay. Let's combine our i's together. So that'll be negative 18i. I got 15i squared and then 24. Now, I squared. At the beginning of this video, I talked about I squared. Oh, it was equal to something special. Take a look in your notes quick. I squared was equal to negative 1, right? I squared was equal to negative 1. So technically, this piece right here, that's 15 times a negative 1, because I squared is just a fancy form of negative 1. AKA, this is negative 15 here, right? AKA, I got to add these two together. So I got negative 18i. Oh, that should have been a negative 15. Whoops. Marsh messed up. Oh. Boop, boop. Silly Marsh. Negative 15, negative 15, positive 15. So let's add 15 and 24. That is an answer of 39. Whew. Almost messed up there. Dodged a bullet. What about raising i's to an integer power? So, I squared is not the only exponent you'll ever raise I to. Sometimes you'll find I can be raised to very large powers, and you're going to have to be able to simplify them. So let's talk about each of the smaller ones first. I to the 0, you might remember back to Algebra 1, your exponent rules. Anything to the 0 power was 1. Then I to the 1st, well, that's just I, which is the square root of negative 1. 1 to the 2, 1 to the 3, 1 to the 4, 1 to the 5, 1 to the 6, 1 to the 7, 1 to the 8, 1 to the 9, 1 to the 10, 1 to the 11, 1 to the 12, 1 to the 13, 1 to the 14, 1 to the 15, 1 to the 16, 1 to the 17, 1 to the 18, 1 to the 19, 1 to the 20, 1 to the 21, 1 to the 22, 1 to the 23, 1 to the 24, 1 to the 25, 1 to the 26, 1 to the 27, 1 to the 28, 1 to the 29, 1 to the 30, 1 to the 31, 1 to the 32, 1 to the 33, 1 to the 34, 1 to the 35, 1 to the 36, 1 to the 37, 1 to the 38, 1 to the 39, 1 to the 40, 1 to the 41, 1 to the 42, 1 to the 43, 1 to the 44, 1 to the 45, 1 to I squared, well, that's just negative or square root of -1 squared, which is 1, or -1, excuse me. We talked about that earlier. What about I cubed? Well, that's just an I squared times an I, right? And we know I squared is equal to -1 times I. So it looks like I cubed is equal to a negative I? Really? Simplified? I to the 4th, well, that's 2I squareds multiplied by each other, right? AKA a -1 times a -1, which is 1. Huh. These two are matching. I wonder if I to the 5th, well, that's just an I to the 4th times another I, right? And I to the 4th, we know that's 1 times I, so that's I. Huh. We got a matchy-matchy thing going on here. And that is always gonna happen, guys. When raising I to any power, the only answers you could ever, never, ever have, you can only have 1, I, -1, and -I. Those are the 4 answers when you're raising I to just a power. Those are the only 4 answers you can ever have. Another way to think of these, because you're going to not just simplify I to the 7th, and you don't want to have to keep breaking it down. You can divide the exponent by 4, and whatever your remainder is, you can figure out what your answer is. Let's try a couple of problems here. So we got I to the 5th. We talked about this a little earlier. We know this is just an I, but let's take the 5 and let's divide it into 4. Then we go 4 is, there's 1 4 in 5, so 4 times 1 is 4, subtract, and that means my remainder, the leftover, after I can't divide anymore, is 1, aka my answer, 2I to the 5th is I, because my remainder is 1, it's I. I to the 23rd, so let's take that 23, divide it by 4, let's see how many I's are left behind. 5 4's go in there. So my remainder is 3. There are 3 I's left behind, aka I cubed is left behind, which means my answer will be -I. And then I got -3I to the 56th. Let's just wait with this -3 here. Let's figure out I to the 56. So we're going to take 56, divide that by 4. 4 goes into 5 once. Take the 16, drop it down. 4 times 4, that's 16. Notice, guys, no remainders, aka there are no I's left after I divide by my 4 a bunch of times. So that means I'm going to have 1 for my answer. So -3 times 1, which is good old -3. Notice last time we talked about, when we just talked about operations with complex numbers, we didn't do division. Division is a little bit of its own little beast. Ultimately, you can't have I's in the denominator. It's a big no-no again. I know, there's a whole bunch of no-nos. But what you're going to do is you're going to multiply both the numerator and denominator by what's known as the conjugate. AKA, you're going to switch the sign between the two terms in the denominator. Then you're going to distribute, multiply, whatever you need to do, simplify your I's, combine some terms, and then write your answer in the form. I know it looks confusing. It's actually not too bad. These steps are a little wordy. Let's try an example. So I have 3 over 4 plus I. What we're going to first do, we can't have this I in the denominator. So what we're going to do is we're going to multiply the top and the bottom by a very fancy form of I. And that fancy form of I is explicitly chosen to be the denominator, but with the sign changed in the middle. Why? You'll see in a moment. It will actually make our I's cancel out. So let's multiply the 3 into their numerator here. So that would be 12 minus 3i. And then let's distribute our denominators here. Put some parentheses. 4 times 4, that's 16. 4 times negative I is negative 4i. I times 4, that's a positive 4i. And I times negative I, that's negative I squared. Oh, look at that. Negative 4i and a positive 4i. Those guys cancel off. Woohoo! That should always happen. Keep that in mind. If this does not happen, if your I stuff doesn't cancel off in your denominator after you multiplied, you done diddly messed up somewhere. I squared, we've talked about that already. That's just a fancy form of negative 1. So technically I am subtracting a negative 1, aka adding 1, right? So on my denominator in that fact, I have 16 plus 1, which is a big old 17. We still have that 12 minus 3i sitting up there. And then we're going to break it apart into its two pieces, just in case sometimes these do simplify down. This case they did not. However, sometimes you'll find that the 12 over 17 will be like 12 over 30, and you'll take a 2 out of both of them, or a 6 in that case. So always break it apart so you can make sure you don't simplify any further. And with that, that's the end of this video. See you later, Sabers.